Is there a class scheduled tonight? I know that the test was moved.
Whoa.
Yes. Yes, it is class scheduled tonight. We're covering the last chapter that we're going to cover. And then I've actually got some information regarding Monday and all that good stuff. You should not need to see Mr. Mitchell on Monday. There is a test, but you have some time to get it done. So I'm in the process of sending an email out to everyone now about that. I want to make sure I logged in early enough, though. I can get my window in the right spot. That would be helpful. Got that there. Okay. Josiah Peterson and Joe. This is literally the first time I've noticed that I've got two Josiahs. I may or may not have had a stroke at some point recently. Sorry about that. Not realizing that. I'm quite an idiot. But anyways, I'll notify all students. PHY 241 N01C. Let me see if I can turn to my pages now and make sense of what I have done. Okay, course modules. So test 5 is due, that's on chapters 10, 11, and 36. That's due by July 24th. That's an online test. I'm not requiring respondus or anything like that. It's just a normal online test. You get multiple attempts, that sort of thing. Test 6, on the other hand, it is going to be a respondus lockdown browser with webcam test. So you've got to be able to run respondus. You can use whatever computer you want, but you got to be able to run respondus lockdown browser and the webcam. If you don't have a webcam, you need to probably use a computer on campus or something like that that can do it. You may have to make sure, if you're using a library computer or something like that, you might have to make sure that they actually can run respondus lockdown browser, and you can talk to TCC info regarding that. And I can also help you if you have any problems. But to prepare for that, I created a practice test 6 just for you to prepare for it. But I created another practice test 6 that has a respondus lockdown browser on it. So let me pull that one up real quick. So there's another version of a practice test 6, but you'll see it includes 14, 15, and like 43 and 44 or something. But it also requires you to do the respondus lockdown browser. So that's for you to just make sure your computer can run the respondus lockdown browser and all that stuff. That will be in a module called practice tests. And you have until, that doesn't seem right, that date. I have to fix that real quick. We got more people coming in. Hold on, let me get them. Admit that. All right, we still got about 3 minutes before class starts. The date on there was funny, so I had to fix that. So as I was saying, the current situation is, and I'm actually writing an email to everyone now, and then I got to send a separate email to Mr. Mitchell, but, oh yeah, that's stupid. But saving, basically I got to send an email to him that says the same thing that's saying to you. And what that is that we have a test 5 that's an online test, like a normal online test. You don't have to have a respondus lockdown browser or anything like that. The practice test is available for that. practice test 5, chapters 10, 11, and 36 until July 25th. If I remember correctly, I want to say that's Sunday. But the main thing is it's July 25th. And at that time, the practice test will disappear, and you actually have to make sure you've completed the actual test, which is test 5, chapters 10, 11, and 36. Again, all your attempts need to be completed on that day, which, as I said, was July 24th. Right either. Let me double check, see what day that is. I meant for it to be due by Sunday. Let's see what that says it's due. 24th. Yeah, 24th is Sunday, so that's what it's supposed to be. So that's fine. The practice test is actually due a day late by mistake, but the main thing is the practice test has to be done. The actual test has to be done by this coming Sunday at 11:59 p.m. So that's test 5. Then test 6, which will cover chapters 14 and 15 alone, and chapter 15 we're covering tonight. There's a practice test for that says practice test 6, chapter 14, 15, and 43 requires Respondus lockdown browser and webcam. You don't want to actually take that. You just want to log into it, download whatever software you need, actually install the software that you need, and then you want to actually make sure that software runs, make sure you can get into the test, make sure your camera works, make sure you actually know the rigmarole of what's supposed to happen when you take a Respondus lockdown browser with webcam. Once you've got that worked out, then you just want to take practice test 6, chapter 14 and 15. That's just a regular practice test. You don't have to do anything special to Respondus, but the practice test that has 14, 15, and 43 is purely for you to make sure you can get your Respondus lockdown browser to work and make sure you can get your webcam to work and all that good stuff. So that's why that's there at all. I would recommend you do that immediately tonight. Say, if you don't do it tonight, do it first thing tomorrow. If you wait to the last minute, you're almost certainly going to miss that last test and get a 0 on it. Then test 6, chapters 14 and 15 is due by 11:59 p.m. on August 1. That requires the Respondus lockdown browser and webcam. That's the whole purpose of you making sure your practice test 6, chapter 14, 15, and 43, which requires the Respondus lockdown browser and webcam. That's the whole reason I put that up there, so you can get that done. Our final is going to be either on the 3rd, and this is up to you. If you want to take it on the 3rd, you can. If you want to take it exactly 1 week later, you can as well. Or excuse me, 1 week earlier, you can as well. So I think that's the 27th and actually, let me check my calendar so I don't have to say I think that. Yeah, July 27th during your lab, you can take it, or you can wait and take it August 3rd during your lab time with Mr. Mitchell. Those are your 2 times taking the final. I'm in the process of sending you and Mr. Mitchell an email about that, but that's basically it. We just reached the actual time for class to begin. It looks like I have only about 8 of you in here. That's sort of enough, but at the same time, I want to make sure. Does anyone have any questions about that? I know some of you just came in.
Yeah. So, the last thing I heard was that we have to have a lockdown browser webcam sort of thing. Is that for this upcoming online test that's due
No, not for
Monday?
that. No, it's due. It's for the next one. So test 5, which I already put out, and you've had time with the practice test for a while with that. That's due technically on Sunday at 11:59 p.m. That one's just a regular online test. You're allowed to do searches of the internet. You're allowed to use your notes, your book. You're allowed to use even Chegg if you find it. Your time's sort of hampered, but other than that, you're just free to do everything, hopefully, and you even get multiple attempts at it.
Oh, so that's due Sunday then. So that changed from Monday to Sunday.
Yeah, I moved that back. It was due, actually, I think it was due like tomorrow or tonight or something like that. And I changed it to Sunday coming up. That was test 5, which is on chapters 10, 11, and 36.
36. Okay. And then the next, so we're going to have 3 separate tests. So we have that test coming up Sunday, and then we have our test after that.
Right. Your test after that will be actual test 6. But before you can do that, you actually have to use the Respondus lockdown browser and webcam.
Okay.
So to
Right.
give you practice with using that, you'll notice now on the top left-hand side of your Canvas page, there will be a link that says lockdown browser. You can go there, or you can just click on, you'll see PT 06, chapter 14, 15, 43, requires Respondus lockdown browser and webcam. I don't want you wasting any time taking the actual test part of that. I mean, you can, it's just going to include elementary particle physics, which is what chapter 43 is. The main thing for you to do that is just to get through the Respondus lockdown browser stuff so you'll know what to expect.
Okay, so we get the software for it, and then we take the quiz, and it doesn't matter what we do or like what score we get.
Yeah, exactly.
Okay.
Now, once you've got that done, I recommend you do that either tonight or first thing tomorrow. Once you've got that done, you'll see there's a practice test, PT 06, chapter 14 and 15. That's the one you want to take a bunch of times before you actually take test 6.
Right. Okay. So test 6 is next Wednesday.
And actually, it's due by next Wednesday. You can take it anytime you want. And this one, I only give you 2 attempts. But I give you a full 60 minutes. But because you got the lockdown browser, you're not allowed to surf the web. You're not allowed to use notes. They ask you to film the area where you'll be working. Show the front and back of all documents that you have next to you, because you are allowed equation sheet, that kind of thing.
Okay. All right.
Does that make sense?
And then we have our final the week after that.
You have your final, and that's by choice, either July 27th, which is next Wednesday, or August 3rd, which is the following Wednesday.
Okay. Thank you. That clears everything up.
Yeah, I'm sorry about all that confusion. I was actually making these decisions today, and I had 3 students making up tests, and they were coming to ask me questions, and I had other students that wanted some help with homework, and I made a whole cluster poo-poo out of it. So what's that harsh language? Cluster poo-poo. Does anybody else have any questions? Was that Gabrielle I was talking to? Gabriel?
That was me, Nora. Oh, I think Courtney was trying to ask something as well. But
okay. Someone else have another question then? Gabriel, did you have a question?
I was just asking the same things that Nora was asking.
Oh, okay, gotcha. I'm going to put that in. Well, you can see it if you actually go to the practice test module in Canvas. And if you go to the test module in Canvas, you'll see the actual dates on there. That's really the relevant part. But I'm going to send it in an email today and send it to Mr. Mitchell so he'll know as well.
if you need me, just let me know.
Any questions?
Nora, your mic is still on.
Yeah, crazy Nora. Get it straight, man.
For practice, I know a lot of us were having issues with the questions populating. Is that something that got fixed?
Yeah, I'm not having any problem with it on my side. Who else is having problems? I got your email, and I got one other person's email. They were having problems, but everybody else and me didn't have any problems whatsoever with.
I'm still having problems with the questions aren't there for me as well.
Okay, what browser are you using?
Chrome.
Chrome, that's the one I'm using. And did all of y'all try emptying your cache?
Yeah.
And it still didn't work after that?
Not for me.
Man, okay. You're going to need to contact TCC Help Desk, because the fact that it works for anybody means it's something with your system that's unique. I don't know why. I even get that to work, for instance, when I'm using a Kindle or an iPad. So it's really odd for it not to be working. Not that there's anything wrong with you or anything, just something's going on with your computer that's not letting that happen. So I would contact the info desk, and they can put you in contact with technical support, and technical support should be able to figure out what's going on with that, because that's definitely way beyond my pay grade, or at least the knowledge base.
Concept 36 is still showing up as past as well.
Concept 36 is showing, okay, that's a date thing, and you're talking about that's in my lab and mastering. Let me write that note down.
Correct.
Concept 36 late. And now, just so we're certain, you guys are talking about actual practice test 5, or are you talking about test 5? that doesn't show question?
Practice test 5.
Okay. I'm going to make a note of that too, so I can double check. I just checked it again today, so it should all be fine. Like I said, I did it with my iPad, I did it with my Fire tablet, and then I did it with my Kindle. Well, that's the Kindle Fire, same thing. And I did it on Firefox and Chrome. So I don't know what's going on. I don't know why you wouldn't be able to see it. Here, let's do this. Let's do share screen. Let's take this guy. Let's say share. And this is practice test 5. I want to show you from my side what it looks like, assuming it all opens and everything was done. Of course, this will be the time that it doesn't work, but that's all good. Okay, so I'm going to say preview. And it shows the 9 questions over here. See, it pops up on mine. When you get to this point, it doesn't show anything.
No, we just when I start the test, there are no questions.
Huh. And it's this one, PT05, chapter 10, 11, 36.
Yeah,
How do you get to it? Are you going through grades over here? Or are you going to modules?
I go to modules.
Okay. And when you go to modules, you then go to what, practice test, or to the link in the
It's gonna be in week like week 8, I think. or week
okay, that
9.
might be the problem. Here, I'm looking at week 8. This is practice test 10, 11, and 36. But that one, notice that one had a date of July 20th.
Yeah,
That's 2 separate tests. That's the problem. I don't know how that happened, but let's do this. I don't think it'll let me unpublish it. It did not. So what I'm going to do is I'm going to remove this. Your grades are still there, those of you who did it there, but feel free to take it some more over in this other one. So let's try using that one and see if you see it. I think it's because I changed the date on this one, but I didn't, or excuse me, on this one, but I didn't change the date on the other one. And I didn't even know there were 2 versions, so that's why I didn't do that. Did that work for you this time? Not rushing.
I'm doing it right now. Yeah, I see the questions now.
Oh, good. Okay, so it wasn't anything technical. Everybody else that had that problem, please make sure you try that. I think that'll work. So go to this module up at the top, which, by the way, you guys hadn't seen until just now. I literally just opened it, so it's not like you're crazy or anything. I think what happened was because I had it at 2 different places when I modified it. I had modified it here, and even though it has the same name, it's treating it as 2 different objects, which I thought Canvas had fixed, but evidently they have not, because it didn't do that. What you'll see here is here's practice test 5. That's the one you're supposed to be taking. Here's the Respond This Lockdown Browser one that you're just supposed to get into and get to the beginning part, read the instructions, all that stuff, and then not touch again. And then here's the one that you want to take repeatedly to prepare for the actual test that is right here and needs to be done by August 1st. I think with that one, I chose to give you 2 attempts, and the 2 attempts have to be done by 11:59 p.m. on August 1. Anybody else have any questions? All right. So, oh, I just made you guys disappear. So we're doing chapter 15 now. Let me give you a little intro to that. And I'm going to do so by sharing the screen again. Here it is. Maybe. Okay, there it is. So this is chapter 15. It's called wave motion. And wave motion is like simple harmonic motion, but simple harmonic motion had a variable, let's say theta or x or y, that varied in time. A wave has a variable, let's say the wave height, which might be y or x or something like that, but that was a function of not only time, but also space. So if you have something repeating itself in space and time, like oscillations do, and it carries energy from A to B, from one place to another, in other words, without necessarily carrying matter, then you have what's called a wave. And that's the hallmark of a wave, is it's an oscillation that repeats itself in space and time and carries energy from one place to another, but not necessarily matter or anything else. So you might think, well, an ocean wave, that's a wave, but that carries water from out to sea into the shore. But you'd be incorrect in stating that, because if you actually go out, let's say on one of the few very rare days that we have, either on the coast of North Carolina, near the beach, that is, or the coast of Virginia, again, near the beach, where the water's actually clear, then you might look out and get in, say, 8-9 foot of water and look down and you can see the actual details of the bottom. If you do that, what you'll see is when you look down and a wave's coming to you, you'll feel the wave pulling you towards it. And then as you approach it, you ride the top of it, and then it goes by and you're left back here. What you'll notice is if maybe you focused on, say, a piece of litter on the bottom, or maybe it was a hermit crab or a pair of skate eyes because it had buried itself under the sand or whatever. What you would have noticed is that you in fact moved out to sea as the wave was approaching you, and then you were lifted up, and as you got to the top of the wave, you then started being pushed into shore and started to move down, and then moved back out to sea again until the next wave come. So what happened was you actually went in a circle. And that's what waves do, water waves do. Water waves, ocean waves particularly, are really two types of waves. They have a longitudinal component that makes you go out to sea and then back into shore, out to sea and then back into shore. But they also have a transverse portion that makes you go from, just 3 feet above the bottom to 8 feet above the bottom, and then back to 3 feet above the bottom. Right. So transverse waves are waves in which there's oscillation, but the oscillation is perpendicular to the propagation. There's two fancy words there, oscillation and propagation. Oscillation just means a repetitive motion, and propagation means the wave is traveling, but they usually only reserve it for waves. But you can see propagation of nuclear weapons. Another word they often use would be proliferation, but sometimes people use the word propagation. Propagation of rumors. That's other times where they use the word propagation. But in terms of a wave, it just means the direction it's traveling or that it's traveling at all. So transverse waves oscillate perpendicular to their velocity, perpendicular to the propagation. Now, the longitudinal part of that, which basically required you to be pulled out to sea and then in towards shore, and the wave was actually traveling in towards shore. So that's what a longitudinal wave does. It has a oscillation that's parallel to the velocity, like that. Okay, that an example of that, for instance, is a sound wave. If you actually look at a speaker for a car, for instance, or in a stereo, what you'll see is the speaker's a round thing. It's got sort of a membrane made out of a cardboard type material. And then on the back of that, you'll see that has been glued a electromagnet. And that electromagnet, of course, it'll even either be a magnet or it'll be electromagnet. If it's electromagnet, you'll have wires connected to it. But then there could be another magnet inside, and then that magnet would have wires connected to it if that one doesn't. But either way, as a particular sound comes in, that would be a peak in the current in a particular direction, and that would cause the two magnets to attract each other, and that diaphragm, that membrane, would go from being like this to being pulled towards the actual magnet. And then if the current went the other way, it'd be pushed the other way. And you might imagine, if you think about the air molecules, if the diaphragm or membrane, say, is just like this, and then all of a sudden it gets pulled this way, what you realize is some of the molecules will move with the diaphragm, but the vast majority of them are going to stay right where they are. So you now have an area roughly from where the diaphragm was to where the diaphragm is now that has a lower density number of molecules. In other words, that volume of space has less molecules of air than it did before. That's called a rarefaction, R-A-R-E-F-A-C-T-I-O-N, rarefaction. Okay. Now, followed by that would be the membrane or diaphragm being pushed this way, and it actually would extend beyond flat. And in that case, you jumbled up all the atoms or molecules next to each other, and that's called a compaction or compression. We don't normally use the word compaction for that. So what you just saw happen was first a rarefaction was created, and then the diaphragm was sent the other way, pushing the rarefaction along, and in fact, behind it, creating a compaction. So you see there's a rarefaction, a compaction, rarefaction, compaction, and it'll go like that all along the wave. The wave, however, is propagating that way, but the oscillation and the density of the molecules or atoms is actually oscillating along the same direction, in the plus or minus x direction. So that's a typical longitudinal wave. As I said, the ocean wave has both of them. Earthquakes have both of them as well. And I always forget which one's which, but I'm pretty confident the P wave, also called the primary wave, is in fact the longitudinal component. And the S wave, which is also called the secondary wave of an earthquake, is the transverse one. Okay. So when an earthquake occurs somewhere on the earth or within the earth, it often happens below the surface of the earth. Those waves propagate out in every direction they can, and they try to choose a path of least time. And the velocity of, a wave through rock depends on the bulk modulus of the rock that it's going through and the density of the rock that it's going through. So as the different types of rock get more dense or have a more rigid structure, the speeds change. So the actual earthquake will follow curved lines. Now, if you take a particular earthquake and detect everywhere on Earth, you can detect that earthquake, then that can give you some idea of what's inside the Earth, because the S waves, which are also called shear waves, they're the longitudinal part, and they cannot propagate through liquid. Everybody hear that? The S waves, which are again, I'm trying to remember, and I hope I'm right, but either way, there's one that's longitudinal and there's one that's transverse, and I'm about 99% sure the P wave is the longitudinal and the S wave is the transverse wave. But the transverse wave cannot propagate through a liquid. Does anybody have a problem with me saying that? Y'all see an issue with that? What I'm hinting
Can you repeat what you said again?
Yeah. So what I'm telling you is the S wave is that if that isn't indeed the transverse portion of an earthquake wave, the transverse part of it cannot travel through a liquid. And I'm asking if anybody has any problems with that, or y'all see any contradictions with that, or anything of that sort. So what I'm trying to hint at is we just talked about ocean waves. What do ocean waves travel in? Would it be a liquid or a solid?
Liquid.
It is a liquid. But do you notice that the ocean wave travels on the surface of the ocean, whereas I'm talking about through the ocean? Turns out there's a real big difference between waves on the surface of an ocean versus waves going through. So if you tried to send me a wave and you and I are both scuba diving, we're underwater, and you try to send me a transverse wave, you can't do that. The reason being is a transverse wave traveling through the water needs to have, for instance, a molecule right here that when it moves up, it compels the molecule next to it to move up too, and the molecule on this side to move up too. If it doesn't, then it has no ability to oscillate this way while it's traveling that way. However, when you look at the surface of the water, you have a molecule here. Are y'all seeing that little picture of me? Because this might be a time where I should probably turn it back to the camera of me. Let's do that. Let's do stop share. Okay, so this is the surface of the water, and you can imagine there's a molecule here, and then there's a molecule on each side of that one. This molecule is pulling the middle molecule that way. This molecule is pulling the middle molecule that way. And then there's a molecule down here and here that's pulling the middle molecule here. And there's one over here, it's pulling it that way. And then there's one below it that's pulling it that way. So if you go to try to pick up that middle molecule, since this molecule that was to its left and this molecule that was to its right had a pull on it, they're going to come up with it. But if you look at water way under the surface, you have this molecule, 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 this, all those forces cancel each other out. And if I go try to pull up one of them, it's not going to bring the other ones with it. So that's why it's okay to have a wave on the surface of the ocean that is a transverse wave, specifically because there's something called surface tension that only exists at the surface because of that asymmetry and the molecules along the surface. The molecules on the surface only have molecules on one side of it down here. Well, could say two sides of it, but there has a plane where there's no molecules on the other side. So this molecule compels the molecule next to it to come up and the molecule on the other side of it to come up. And then that molecule does the same thing to its neighbor. And then that molecule does the same thing to its neighbor. So you can actually get a transverse wave.
I have a question. Oh, sorry. At what point does a transverse wave switch to becoming like a compression wave underneath the water? Because like I'm thinking the single layer of atoms that covers the surface of water is what is the transverse wave, but everything else underneath of it technically falls under compression.
Yeah, so really, to be honest with you, the only place the transverse wave is acting is on the surface.
So just that first layer.
Yeah, more or less that first layer of molecules.
Interesting.
You might be able to argue a couple layers just because, the structure of how water molecules group might be such that the second layer is only half as far again as the first layer. But yeah, not too many of those. The weird thing is, though, you can get that compression. So for instance, if you happen to be scuba diving, if you know about scuba diving, the deeper you go, the higher the pressure gets. And in fact, at zero depth, you have 1 atmosphere of pressure. If you move down to 30 feet of salt water, you have 2 atmospheres of pressure, one from the water and one from the atmosphere above it. And if you go down to 60 feet, you have 3, and 90 feet, you have 4, and 120 feet, you have 5 atmospheres of pressure. But imagine this, imagine you're out in the ocean and you're down at say 50 feet. And then all of a sudden this wave comes by, and the wave, of course, has a peak and a trough. Well, if the trough comes by you, then all of a sudden you might go from 50 feet of depth to say 40 feet of depth.
Wait, how would that work though? Because isn't transverse waves are like they transfer energy like in a linear way, right?
Yeah, they go left and right.
But if you're underwater, wouldn't it just push you a little bit like to the side? It wouldn't necessarily push you up.
Exactly, and you probably wouldn't feel very much pushing to the left and right. That normally comes from underwater currents. But what you would feel is that the weight of the molecules that are on top of you, which is what's causing that pressure of 3 atmospheres, say,
gotcha.
That just got lower. You got closer to the surface strictly because the bottom of a trough of a wave was over top of you. So it's like you ascended from 40 feet, from 50 feet to 40 feet. Okay, and then all of a sudden you get to the top, the peak of the wave, that's over top of you. Now you went from 40 feet back up to 60 feet. So you can imagine if you're actually in really rough seas, there would be a time delay for all that to happen, but still it's not necessarily a safe situation because one of the rules of scuba diving is never hold your breath, never hold your breath, never hold your breath. So the brief second that you typically might hold your breath just by, maybe you're straining to pick something up, you found a cool piece of artifact that you wanted to get. So you just held your breath for a split second. If a wave comes flying by you, and reduces your depth by 10 feet in a split second, your lung could pop and it could be really problematic. So that's sort of the neat and questionable aspects of the fact that the water depth changing as big waves go by. I always just stuck to the rule is I don't want to scuba dive if the waves are much bigger than about 7 feet. So not necessarily from seasickness, but from that worry I have because I'm a hypochondriac. So I've never heard of any stories of that, but I did ask all my dive instructors and they're like, well, that sounds right to me. So anyways, but yeah, so that's how that works underwater. If you want, in fact, to signal another person when you're scuba diving, if you happen to scuba dive, you'll know that one of the things you can do is you can keep a wrench on you and you hit your scuba tank and it'll make a tack, tack, tack kind of that loud noise. That's really awesome. You can notify your friends, but the problem is, as we'll learn in a second, the velocity of waves through or in material is always equal to like the square root of some elastic measurement divided by, again, all this whole fractions under the square root, but it's like the square root of some elastic measurement of the material that the wave's going in or through divided by say the actual mass or density of the material. So in an ocean wave, for instance, the ocean wave, I should say a sound wave in the ocean, that's velocity is equal to the square root of the bulk modulus of water divided by the density of water. Well, I know most people don't know this, but as a nerd physicist that I am, I happen to know that the density of air is about 1.24 kilograms per cubic meter, whereas the density of water is 1,000 kilograms per cubic meter. So it's literally 1,000 times more dense. So if you're thinking velocity is equal to the square root of something with density in the bottom, and the density went up by a factor of 1,000, you'd say, oh, wow, that looks like the speed of sound is going to be a lot slower underwater. Well, the problem is the bulk modulus of air is almost nothing. It's a tiny number, whereas the bulk modulus of water is huge. So it turns out that the speed of sound in water is quite a bit faster than the speed of sound in air, because that bulk modulus more than compensates for that increase in density. Therefore, you can look up the factor yourself. It's been a long time since I looked that up, but it's on the order of like 5 or 20 times faster or something like that. But what that causes is normally, like if you're over there and you tap your tank with a wrench, what normally happens in the air is my ear detects the sound hit this eardrum, and then a millisecond later or so, the sound gets to this eardrum, and my brain says, oh, not only did it get to this eardrum first, so I know she's on this hemisphere of my thoughts, right? But it also sort of hit sort of in the frontal region. So that made me feel like maybe she's even up there ahead of me. Well, when the speed of sound is so much faster, your brain can't discern the time difference between those things. And all sound underwater is what they call omnidirectional. So that's why you can't actually detect the direction of sound underwater. So if your friend's trying to warn you, hey, there's a great white getting ready to eat you, all they can do is just let you know that there's a great white. You can't really you can't really figure out where your friend's coming from. You just say, oh crap, somebody's trying to get my attention, so let me start to panic. Well, obviously you don't want to panic. It's a fight or flight. I would suggest you think, and that would be your version of fighting. Normally the shark's not going to bother you though. Any questions on that part? Okay, so this is chapter 15. I'm going to talk about waves on strings. I'm going to talk about waves on ropes. I'm going to talk about waves tied to hooks on the wall, all sorts of cool stuff like that. I'm going to give you the fundamentals of waves. For instance, if you look up here in this diagram, wait a second, y'all might be able to look at it if I'm going to do that. Let me do share screen again. So if you're looking at this diagram right here, you see the person holding their hand. This part of the wave up here at the top is called a peak, of course. And this part here at the bottom is called a trough. And if you imagine the wave being like a perfect sine or cosine wave, then there would be like a midline that's horizontal, that's halfway between the top and the bottom. That distance from that midline perpendicularly up to the peak or perpendicularly down to the trough, that distance would be called the amplitude. So that's a key parameter in waves as well. If this wave we're going to the right and we're watching it, and we're watching, say, this particle right here by his thumb or her thumb, whoever that is, right? If we watch that particular particle, what we'd see is that particle would do something like this, and then come back right to here. And that is, in fact, a whole wavelength. Notice it's sort of the upside down of a sine wave. So a sine wave is an archetypal envisioning of a actual wave, a full wavelength. A cosine wave is also one, and that goes from peak to trough back up to peak. So if we watch this particular particle at the peak here, it would go down, 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 come to a stop, go up, 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 and come to a stop. And we'd say that wave, that portion of the string has now went an entire wavelength as I watched it. Okay. So the wavelength measured in inches, feet, meters, miles, centimeters, whatever, that is a unit that we deal with in waves. The amplitude, which can be in all sorts of things. For instance, if we're talking about a wave on a string, the amplitude's in inches or centimeters or meters. If you're talking about electromagnetic wave, the amplitudes in volts per meter or newtons per coulomb. If you're talking about the magnetic portion, it's in Tesla. Or if you're talking about a pressure wave, it's in newtons per square meter. So there's all sorts of units the amplitude can have, but the wavelength is the minimum distance you can travel over a wave structure such that the motion starts to repeat itself. So we could say, let's say halfway between the midline and the peak right here. If I go halfway between the midline and the peak, that's not quite a wavelength. Notice to the right of this point, it's sloped up, but to the left of this point, it's sloped down, and to the right of it, it's sloped down. So you can see that those are clearly not equivalent points. So if you take, again, halfway from the midline to the peak and choose that point, you'd have to skip this one. But when you got to here, you know, oh, well, that's a wavelength. Because now not only is it the same height, but if I look to its right, it's sloping up. If I look to its left, it's sloping up towards it or down away from it. Okay. So those are wavelengths. Again, we in the SI system just use meters, but like I said, any unit of length would work, miles, all sorts of stuff like that. Now, if you were to watch this wave go by, and let's say we're going to watch this specific point on the spring, which is right here on the string, which is right here where the midline crosses the rope. Okay, what we'd see is that midline, that particle on that rope would essentially go up, reach a peak, go down, reach the midline, stop, reach a trough, and then come up, and it's now completed one wavelength. And if we were timing that amount of time would be called the period, which is indicated by a capital T as in Terwilliger. Okay, so that's a T, the period of a wave. It's just like the wavelength, only it's in a position versus time graph or amplitude versus time graph instead of a amplitude versus position graph. So a wave travels a distance of one wavelength in an amount of time equal to one period. And from that, we can get a very useful equation, which I'll deal with in a second. So you've now seen, of course, that the parts of the wave, the trough, the crest, the midline, the amplitude. If you're a surfer, if you're sitting down here at the bottom of this part, you look up and you'd say, oh, crap, the top of that wave's 10 feet higher than I am. You would call that a 10-foot wave, but we in physics would say that wave has an amplitude of 5 feet. Does that make sense? Any questions on that? Okay, and we already talked about with oscillatory motion last time that the frequency which is a number of cycles that pass you by or pass a particular point in space in a single second. That is 1 over the period, and that same relationship holds here. Okay, so here's how you see the period, the characteristics of wave motion and the actual characteristic parameters of wave motion: amplitude, frequency, period, velocity. I even told you a way of calculating that a second ago. And if you read these paragraphs, he actually gives you a really good description. He even does a derivation of imagining a single part or a single particle of this rope and imagining the forces on it. And lo and behold, it comes up and derives a wave equation. I'm not taking the time to do that for you, but it's nice because I am going to show you what a wave equation is, and that's something we can use over and over again. So here's all the parts that I told you about: crest, amplitude, trough, wavelength. Again, the period is the time that's required for a single wavelength to pass a single point as the wave is traveling. As I said, since the distance the wave travels is 1 wavelength in a time period of 1 period, then you'd say wave velocity is equal to wavelength over period. That's what it says right here in the last line before equation 15.1. But we also know that 1 over the period is equal to frequency, so I can replace that division by t with multiplication by f, and that's the famous equation, or the simple version of the wave equation that's somewhat famous and gives you, for instance, the velocity is equal to the frequency of the wave times the wavelength of the wave. We'll talk more about that as well, but that's some of the terminology. Here's the types of transverse wave versus longitudinal. You can see this slinky is oscillating up and down, even though the wave is traveling left and right. That is, which type of wave would you call that?
Transverse.
Transverse. And you can see this one, if you're actually taking the spring and pushing it and then pulling back and then pushing it and then pulling back like that, you get the rarefaction and compression, rarefaction and compression. And that's what it would look like. You sort of see the molecules bunching up right here and then spacing out over here. That being said, the same velocity equals wavelength times frequency. All that stuff still stays the same for waves. What we have found, though, is that transverse waves have the ability to propagate through a vacuum. We initially didn't think that was the case. We know, or we've never found a case where a longitudinal wave can travel through a vacuum. So sound, for instance, can't travel in free space. Now, what happened was when we came up with the idea that electromagnetism, which by Maxwell's equation was shown to be electromagnetic waves. And what I mean by that, it was an electric field, say, oscillating, let's say vertical. Really what the direction it oscillates in the electric field is called the polarization. So if a wave was vertically polarized, the electric field is oscillating vertically. The magnetic field, on the other hand, would be oscillating horizontally such that it would go up and to the right at the same time. The electric field would go up as the magnetic field went to the right, and then the electric field would go down as the magnetic field went to the left. That's always going to work that way. And then a third direction perpendicular to both of those is the direction that the velocity travels, and it's done so such that if you do the cross product of E cross B, your thumb of your right hand points in the direction of the velocity. Okay, so in that case, what you see is actually doing the oscillation. The oscillating is the electric field and the magnetic field. That was what we knew the radiation coming from the sun was after Maxwell's equations were derived. So everybody immediately said, okay, well, there must be something out in outer space because clearly the sunlight's getting to us because we can feel it, right? So they imagined that there must be some matter out there, and they called it the ether. And then they did a really fancy experiment that should detect their motion in the ether, whereas they set a laser beam at 90-degree angles to each other, or 2 laser beams at 90-degree angles to each other. And if you happen to have one of those laser beams lying along the direction that you're going through the ether, then the laser beam is going to slow down when it's going against the ether on the way to its mirror. and then it's going to bounce off that mirror and speed up because now it's going with the ether, speed up back here. And that will mean this wave that was going perpendicular to the ether, this laser is not going to change at all. So the waves, the lights will come back and there will be a delay. And if that delay is on the order of a wavelength different, then you'll get an interference pattern. Well, when they did that experiment, it was called the Michelson-Morley experiment, they found no difference. And ultimately they had to just throw away the whole idea of the ether. In fact, people even made up equations to say that the ether was doing some magical stuff to make the ether still work. And oddly enough, the made up equations turned out to be exactly the right equations. When Einstein created the special theory of relativity, he could derive them as well, but for a really good reason. Namely, the reason was that Maxwell's equations told him that the laws of physics are the same for all inertial observers, and that the speed of light is independent of the motion of the source or the observer. And when he took that into account, he automatically got the exact same equations. So here's the velocity of a wave on a string. Notice the velocity is equal to the square root of the tension divided by the mass per unit length of the string. So if you look at a guitar string or a violin string or a banjo string, cello, any kind of stringed instruments, you're going to see some of them are really fat and some of them are really thin. And the thin ones, in fact, play high pitch notes or high frequency notes, and the fat ones play low frequency notes. Basically, they all have sort of the same length, right? The distance from the nub, which is where the neck meets the little block where the little pulleys are. That nub is the dead end of the string, and then the bridge on the other end is the dead end of the string. And all of those lengths are pretty close to the same. I mean, some instruments, they actually intentionally make it a little bit different, but in general, they're all about the same. So when you pluck them, you get basically an oscillation of the upward direction. And if you time it just right, where when this wave travels over to the right-hand side, gets to the nub, and then turns around and comes back, and the instant that comes back, you pluck it again, then you'll get what's called a standing wave. And that standing wave could be such that you have 1/2 wavelength between the nub and the bridge. If you pluck it a little harder, you could have a whole wavelength between the nub and the bridge. And harder still, you have 1.5 and so on and so forth. Those are called standing waves. But you see, since all the lengths are the same, then that means all the wavelengths have to be the same. But since the velocity depends on the mass, and velocity is equal to frequency times wavelength, the frequency is in fact directly proportional to the mass. And because of that, I should say velocity equals frequency times wavelength, but the wavelength is related to the string's mass, the string's length, and they're all the same. So if you actually solve for the frequency, you get the velocity divided by the wavelength. Well, the velocity goes up as mu goes down. They're thumbs up, thumbs down. So a low mass string is going to cause a high velocity, which causes a high frequency. So that's kind of interesting. But this is where your where your author actually derives a wave equation from the string by treating it as little bits and pieces. And the fundamental idea of a wave equation, I'll draw again for you later, is that you have a second order derivative in space equal to 1 over the velocity squared times the second order derivative in time. Here's some typical velocities. So for instance, for longitudinal waves, the velocity is some elastic force factor divided by some inertia factor. So if you're talking about maybe hitting the end of a rod with a sledgehammer, that's going to cause all the atoms at the end to bunge up against, well, actually you want longitudinal waves. So it's going to bunch up against the next row of atoms, and then that's going to cause the next row of atoms to bunch up, and that's going to cause the next, and so on and so forth. Those longitudinal waves are going to have a velocity given by the bulk modulus, or the elastic modulus E divided by the density of the material. So you take that square root of the elastic modulus divided by rho, and you get that one. If you want to talk about longitudinal waves in a fluid, that's the bulk modulus, which is the change in volume divided by the initial volume and divided by the density. You can find these moduluses in your textbook. We skipped that chapter. You're going to do a lot of it if you're going into engineering. You'll see a lot of moduli, and a modulus is stress over strain. That's the rule. And what I used to help me remember that modulus is always stress over strain. So a bulk modulus is an example, elastic modulus is an example, Young's modulus is an example, but it's always stress over strain. And notice the word stress has RESS in it. Pressure also has the letters RESS in it. So stress, one example of it is pressure. So force divided by area is a stress. And then strain is a change in length divided by length, or a change in area divided by an area, or a change in volume divided by volume. Or it might even be a racking where basically you apply a force to the, let's say, to the front cover of a textbook, and then you apply a force this way to the bottom cover of a textbook, and it shifted so that the pages went like that. That's a shear stress. And in fact, in that case, it's the difference between the horizontalness of the top cover to the bottom cover divided by the length between them. So the thickness of the book. So that's the shear modulus is another example. But anyways, let's go through with these pictures just because I'm going to do that. And then I'm going to give you the sort of the mathematics of it. So here's where he derives a wave equation regarding waves through a fluid. Again, that stuff's not that necessary. These examples are going to be very straightforward. What you do find is that the energy of a wave is proportional to the square of the frequency and the square of the amplitude. That's a fundamental rule in physics, something we can't get around. When you talk about the power, that's energy per time. Notice that is proportional to the density of the material, which makes sense, right? A wind wave might mess up your hair, whereas an ocean wave might mess up your house, right? And so it's proportional to the density, it's proportional to the velocity, which clearly a fast wave is going to do a lot more damage than a slow wave. And again, it's also proportional to the square of the frequency and the square of the amplitude. And then if you do the intensity, which is the pressure per unit surface area, that again is velocity density times force frequency squared times amplitude squared. So those are the things that really matter when a wave is transporting energy, is things like the energy, the power, and the intensity I. Let me look over here a second. The intensity, since it goes like 1 over r squared. So if you have, for instance, let's say my brain is putting out kinetic energy. Okay, it's doing this thing, telekinesis. So I'm sending out messages to the world, and I'm letting, advanced beings read my brain, or I'm sending out messages to the material world and I'm making them move. Okay. Well, if I get far enough from me, say 10 meters away, my head, which is, where my brain is, obviously, my head is infinitesimally small compared to 10 meters. So when I get, let's say 100 meters away, every bit of energy my brain set out will have exactly the same intensity over that sphere that's 100 meters in radius and centered on me. In other words, that's all my brain can do. It's going to, every part of that sphere's surface is the exact same distance away from my brain, from the center of my brain, as every other part. Therefore, the energy I can spread over that is some fixed amount. Now, if I instead considered a sphere centered on me whose radius was 200 meters, so I just doubled it, then the let's say 1 meter by 1 meter window that was on the 100 meter sphere has now become a 2 meter by 2 meter window on the 200 meter sphere. And you see that the intensity, which is the pressure or the energy per unit area, has went down not by a factor of 2, but by a factor of 2 times 2, which is 4. So that's why we get 1 over distance squared. And in fact, it's such a fundamental idea that Einstein was asked this very question when he became famous. When people become famous, they ask them questions about everything. I mean, even, actors and actresses that don't necessarily have any merits in the area of physics or civics or ethics or anything like that. So they asked Einstein all sorts of questions, not only about science, but about other stuff. And one of the questions they asked him is, Professor Einstein, do you believe in telekinesis and the ability to read brains, read minds and stuff like that? He said, if you show me it obeys a 1/r² law, then I'll believe it. That is exactly the importance of this. Whatever portion of energy comes from this source at the center of a sphere, if you go out 1 meter and choose a 1 meter by 1 meter window, all the light that goes, or all the energy that goes to that little window, when you get out to 2 meters, is now going to have to go through a 2 meter by 2 meter window, and therefore will be decreased in intensity by a factor of 4. If you go out to a 3 meter sphere, then that same light will now be through a 3 meter by 3 meter window, and therefore would go down by a factor of 9. If you go through a 4 meter sphere, it'll go down by a factor of 16, so on and so forth. Okay, so that gives you sort of the conceptual ideas that you need for this. Now we're getting into the math part, and that's where I'm going to go ahead and start writing stuff. I wanted to make sure there's no other ideas that I wanted to push here. Well, let me go ahead and get you one wave equation so you can see the form. I'm going to write it several times, of course, but I want you to understand this is, quote unquote, the form of a wave equation. See, you got the second derivative in space. That D is like whatever the thing that's oscillating. So if it's a pressure wave, D might be pressure measured in newtons per square meter. If it's an ocean wave, D might be actual meters, where it's talking about the amplitude. So it'd be Y of X and T. But it's a second order partial derivative with respect to X, and then 1 over the velocity of the wave squared times the second order derivative in time. So that's the hallmark of a wave equation. I'll show you an example where this one happens to be only to the 1 power, but that can only be so if the function D is has an imaginary part and a real part. In other words, if I comes into play. So that's why Schrodinger's equation is a wave equation, yet it only has a first order derivative in time. All right, now that we have that, let me stop sharing screen, at least with that screen, and I'm going to pull open my trusty notes and give you an example, some examples of the stuff we're talking about here. So I'm going to try to hit a little bit of everything, and I'm going over the concepts because really the science in here, the solving the physics problems, is really straightforward. They're all sort of plug and chug stuff. So let me first off start off by saying that I would like to share the screen with my iPad, or my iPad screen with you guys. My nose is okay. I'm going to share, and I'm going to go over here and click on this and pull up my iMac. Okay, and now we're all looking at the same thing. So when I tell you a wave equation in one dimension, and what I mean by that is the wave is going to oscillate in the X direction, and it's going to travel in another direction. Let's say the wave is going to oscillate in the Y direction. Let's do it that way. So the wave is going to oscillate in the Y direction because it's going to be transverse. It's going to travel in the X direction, and it's going to do so over time. So you would say the wave could be described as Y of X and T is equal to some amplitude times cosine. And here's the weird part. It's going to be K times X minus omega T plus phi. I already showed you that the wave equation is a second order differential equation. We talked about that last time. A second order differential equation suggests you're going to have 2 constants to manipulate with initial conditions. So I have to have 2 constants. The one I chose were A and phi. I might have chosen A cosine kx minus omega t plus B sine kx minus omega t. That would have been fine as well because I got an A and a B. But that's going to be a particular type of wave equation or a particular type of expression for a wave. And what it really means is that the height of the wave is given by A times the cosine of kx minus omega t at any particular x at any particular time. Now, that wave can be infinitely wide. In other words, the z-axis is free to be everywhere. So whatever that particular height is, y, that's for all the whole z-axis, and you get what's called a plane wave, which for all intents and purposes you can look at like this. You imagine this going on forever, this going on forever. That's a plane wave. See this crest right here? Imagine that crest going infinitely far into the background and infinitely far into the foreground out of the front of this page. That would be what's called a plane wave. Okay, and I will do you one better and say basically that this could be X and this would be Y, and we're not even showing the t-axis on here, but I'm going to tell you that this wave is in fact moving in the positive X direction. How do I know that? Well, you can sort of say this whole thing represents the phase of the wave. Okay, it sort of represents that whole sine curve that I just drew. Right, for a given X, it's one particular part of the sine curve that I drew. So any part of this little blue line. But if you consider an interval from X to X plus 2 pi, okay, then you're automatically going to have a whole wavelength. And you can see that X plus 2 pi from X to X plus 2 pi for this Kx minus omega t would be an entire whole wavelength, if you will. So because of that, let's say this phase equals a constant. And let's say the constant's going to be c. So what I'm going to say is Kx minus omega t plus phi is equal to c. I want to solve that for x. What I'm trying to do here is convince you that this wave is moving to the right. Okay, so that's to the right is what I'm trying to say there, but I ran out of space. So what I'm going to do is I'm first going to say Kx is equal to, let's say, omega t minus phi plus c. And now I'm going to divide both sides by k. And I'm going to say x, which remember, x represents any particular spot. Let's say that spot right there on the sine wave. So x is, I don't mean to put a colon there. X is equal to omega over k times t minus phi over k plus c over k. So you see, as I really shouldn't write it that way. As time increases, so does x. So what we said is that little point on the wave that I represented with a little sand spur looking thing there, that is moving to the right as time goes up. And in fact, you can even make out that the velocity, what we call the phase velocity, is actually equal to omega over k. Okay, now if you consider another function, let's say y2 of x and t is equal to a2 cosine k2 x plus omega t plus phi, and let's say omega 2 and phi 2. We again can say k2x plus omega t plus phi 2 is equal to constant C2, and we can solve for X. And what we'll see there is X is going to be negative omega T, omega 2 over K2 times T, minus phi 2 over K2 plus C2 over K2. So as time goes up, the X goes down. So this wave is left moving. Moves in negative direction. Okay. So I haven't made really the argument that that is a wave, but it is. I mean, you can clearly make sense that that looks like an ocean wave, right? So that looks like what a transverse wave looks like. And for all intents and purposes, the longitudinal and transverse waves greatly mimic each other. So there's not a whole lot of different things you have to deal with to come up with the behavior of a longitudinal wave versus a transverse wave. They're essentially a lot alike. So we now realize that when you have a kx minus omega t, that's a wave moving in the positive x direction. If you have a wave moving, or excuse me, a wave recognized as kx plus omega t, that's moving in the negative x direction. And then more generally, we would say y of x, y, z, t is equal to sum a times cosine. And in this case, the more general result is we make k into a vector, and we take the vector r and we say minus omega t plus phi. Okay, so k is equal to 2 pi over lambda, like we had just studied before, right? But in this case, it points in, let's say the d direction, and I'll say that's a unit. So I'm going to call that a unit vector. I'm going to say, yeah, I guess that'll be fine. D unit vector, which is the direction of propagation. So you see this k vector is actually supposed to have a magnitude of 2 pi over lambda, but it points in exactly the direction the wave is going. R, the r vector, is just x I hat plus y j hat plus z k hat. So if the wave happened to be going in the x direction, parallel to the x-axis, then k dot r would just give you kx, which is what we were using before. So this is just a more general result for 3 dimensions. And what you really need to know here is the fundamental ideas. K is equal to 2 pi over lambda. Omega is equal to 2 pi times f. F is equal to 1 over the period. That's a period there. And remember, velocity equals distance divided by time. And that allowed us to conclude its wavelength over the period, which is also wavelength times frequency. So you can now see that, for instance, k times x would be 2 pi over lambda times x. And that just tells you as x goes from 0 to the wavelength, then the wave goes from here to here. Does that make sense? Notice how when I do, let's just say pi, I get pi, or excuse me, let's just say half a wavelength. I get wavelength over 2 divided by wavelength, that's just 1 over 2. So that gives me pi, which would put me right here at this part of the wave. So that's what the kx is about. And you can also see that since omega is equal to 2 pi f, when you see omega t, what you're seeing is 2 pi times the frequency times t, which also equals 2 pi over the period times t. So as t goes from 0 to the period, then what we see is that the cosine goes again from here to here, but in time, not in space. So that's why those things are like that. And a lot of this chapter, when you go to solve problems, is just about, okay, let's find out what K is. We'll give you the wavelength and it will tell you what direction it's going. So let's figure out what Kx minus omega t becomes in this general case where it's not necessarily propagating along the X direction. And let's find out what the wave speed is. Well, that brings me to the other part. Remember I said the typical wave equation is equal to this. So by looking at this, you can manipulate it and see that v squared would equal the second derivative of d with respect to x squared, or excuse me, with respect to time squared. Let me erase those two. Divided by the second derivative with respect to x squared. So if you actually are given a wave function y of x and y, z, and t equals a cosine kx minus omega t plus phi, you can find out what the velocity is by taking the second derivative with respect to time, then taking the second derivative with respect to velocity, and dividing the time one by the, or excuse me, with respect to position, dividing the time one by the position one, and then taking the square root of that, and that'll be the velocity. Any questions on that? All right, so that's some of the neat things we can do with the waves. We can make them like that. You need to be able to know, of course, which one's a left going wave, which one's a right going wave, that sort of thing. The other thing you need to know is that that wave equation is linear. So the wave equation is linear. So what that means is the second partial of, let's say, y1 with respect to x squared equals 1 over v1 squared times the second partial of y1 with respect to time squared, and second partial of y2 with respect to x squared is equal to 1 over v2 squared, second partial of y2 with respect to time squared. So if the left equation is true and the right equation is true, then y, well, where did it switch there? Y equals C1 times Y1 plus C2 times Y2 is also a solution of the wave equation. You'd get something like second partial of y with respect to x squared is equal to C1 second partial y1 with respect to x squared plus C2 second partial y2 with respect to x squared. But this part right here, we already saw was equal to 1 over v1 squared second partial with respect to t squared. And this part right here, we already saw was 1 over v2 squared second partial y2 with respect to t squared. So what you see now is that you've got C1 over V1 squared, second partial y2 with respect to time squared, plus C2 or C1, C2, yeah, that was right, over V2 squared, second partial y2 with respect, that was supposed to be 1 over there, with respect to time squared. So let me do this real quick. Zoink. Yep, I just said zoink. Okay. So that's really what we're showing there is, and that's the nature of a linear differential equation, or as I've been talking about before, I've used the dot product and the cross product and made the arguments that they were quote unquote linear, and I'll continue to do that next semester. And that's what that means, is if you have two things that are in it, you can just basically add them together with a and put an arbitrary constant in front of each one of them, and you'll just get the sum of the two acting just like the one by itself. So that's the wave equation being linear, and that gives us this neat little idea that if you have, for instance, two waves and they're going to actually interact, you might have, for instance, this wave looks like that, and this wave over here looks like this, and this one's moving this way and this one's moving this way. What we can do is say, okay, well, if I go 1 centimeter to the left of the end, then I'm going to say this height right here is 1 centimeter, and this distance right here is 1 centimeter. So I'm trying to give it some coordinates, if you will. Now I go over 1 centimeter, this one's going to be 2 centimeters. And then if I go over 3 centimeters, this one's going to be 3 centimeters. So there's 2 and there's 3. And then if I go over here, that's 2 again. And then if I go over here, that's 1 again. This one, on the other hand, might be, let's say, 1 centimeter. But then I go over to 2, and now this one's going to be 4 centimeters. And if I go over 3, this one's going to be, in fact, 7 centimeters. And then if I go over 4, this one's going to be 10 centimeters. And then again, I get 7, 4, and 1. Okay. Now, the only reason I'm doing this is I'm trying to make sense of what happens when these two waves start to run into each other. Okay. What we're going to get there is, this is sort of the drawing of the wave undisturbed, and this is sort of the drawing of the wave undisturbed, but this little part is 0, so that part's undisturbed, but this part right here is going to be taller, so I'm going to go switch to this. This part of this wave has been unaffected so far, but right up to here, this part of the wave right below this starts to add to it, and it gets a little hump like that. And then this part of the wave's unaffected. If we go a little further in time, so okay, then what we're going to see is this wave. Again, I'm trying to draw it exactly like it was before. Obviously, I'm failing miserably at it, but yeah, I think you get the same point. You get the point, right? So this is what the wave's before, but literally directly above it, this is 0. So the wave's unaffected all the way to here. And this is 0 roughly here. So this wave's only unaffected there. But right here, I get quite a big increase. And then here I get a little increase, and then it goes like that. So what's happening is the amplitude at each x is adding exactly with the amplitude of the other wave at each x. And ultimately, what'll happen ultimately what'll happen is the waves will actually separate, and now the big wave will be unaffected. The big wave will act as if it's never been damaged, and the small wave will act as if it's never been damaged and move this way and that way. So that's called the principle of superposition. The word is superposition. Now, this is why if you go out to Rudy Inlet, for instance, and you look and you see a bunch of boats going in and out of Rudy Inlet, they're all going fairly slow. None of them really makes a wave any bigger than, say, 1 foot. But you stand next to the jetty and you might on occasion see a wave that gets some 3 or 4 feet tall. You're like, how's that happen? Well, what's happened is you've had a 1 foot tall wave like this line up exactly with the crest of a 1 foot tall wave and exactly with the crest of another 1 foot tall wave and exactly with the crest of another 1 foot tall wave, and therefore all the amplitudes have constructively interfered. If all the troughs lined up, they would constructively interfere and you'd make a 4 foot deep hole. If, however, the crests lined up with the troughs like this, okay, then you'd get a flat line, which means destructive interference. Okay, and let me put this here just to separate the two ideas. So that's the way, that's what we learn about the wave equation being linear, is two waves are just going to add to each other, amplitude by amplitude. So if, 1 centimeter from the right edge of the wave is 5 meters high, and 1 centimeter from the left of the other wave is 1 centimeter high, then when those two parts line up with each other, it's going to be 5 plus 1 centimeters high. And when it moves over to the next spot, now that 1 centimeter high thing might be adding to a 12 centimeter high thing and get 13. And that's what I was trying to show you with these little drawings down here with the red waves, where they're adding together. Ultimately, what happens is you sort of get in the center, you might even have a scenario which looks like this, where this structure right here in the blue is supposed to be the original wave moving to the right, and this structure right here in the blue is the original wave moving to the left. So does that make some sense? And that actually should happen more like, let's say, over here, not between these two scenes. Does that make any sense? Anybody have any questions on that? It seems sort of highbrow. Go ahead.
Could you show the previous page so that I could take a screenshot of it?
Yes.
Actually, I guess the one before that one. I
Okay.
didn't realize.
No problem. And these are going to be up on Google Docs, so don't forget, if y'all lose that or something, you always have that.
Okay, thanks.
No problem. All right, so what we've learned is that a wave equation has a very specific form. It's a second order derivative in space equal to 1 over the characteristic velocity squared times the second order derivative in time. That's a linear equation, so that means if you find one solution, the sum of that solution, and if you find another solution, that one, those two sums added together is yet another solution of the wave equation. So they're going to act like they're not even interacting. All that literally happens is you're adding the amplitudes point by point for the waves as they interact. And then once they get past one another, they act as if they never changed at all. So you can actually use that to make some sense about how waves travel. So this is a series of examples that I was once contracted by a textbook publisher to write and solve and make up some problems for the LSAT and the MCAT. And I don't know if you know about those. The MCAT's like for medical school and the LSAT's for law school. But they have a physics component on it because they expect you to know some physics. And it's mostly not that they care whether you can, solve for the angle, blah, blah, blah. What they really care about, do you understand the concepts? So they had these neat little questions, which I'll start off with by saying, imagine a rope tied to a hook in a wall like that. Okay. And I use that to make a little wave and try and of course send that little pulse, if you will, to the right. What's going to happen over time is this wave is going to travel like that. And when it gets to this, whoa, Nelly. When it gets to this actual ring, okay, the wave is actually going to try to lift up on that ring. Because of that, Newton's third law says the ring will apply an equal but opposite force in the downward direction on the string, and therefore it'll make the string hump turn upside down, and the hump will come back backwards. Okay. So that's one scenario. Now let's look at another scenario. Let's imagine instead, actually, let's imagine we had a sleeve around here that was essentially frictionless because it had ball bearings on it, and then it had the loop on that sleeve, and the rope went like here, and we had the wave coming towards it that way. Okay, now when the sleeve and ring is reached by the wave is going to pull up on it, and this sleeve is going to move up and down. And in fact, what's going to happen is the sleeve is going to send the wave back right side up. And I'm trying to show these all as exactly the same shapes and sizes. Obviously, I'm not doing that very well, but that's the key point is if you have a fixed connection, the wave is inverted. If you have a moving connection, the wave returns upright. It turns out that's not just a phenomenon of strings. When light, for instance, hits a puddle, say in a parking lot or on a highway, the uppermost surface of that puddle might actually be one type of oil, and that'll have a considerably lower density than water. And then when it gets to the bottom of that particular layer, it's going to either act like a fixed end is what it's running into. It's going to act like a moving end is what it's going to run into, is what it's going to run into. And in fact, the wave will actually change phase at that intersection. So when it hits that next point, it's going to change phase. That's what gives you basically those rainbows of colors you see out in the parking lot. It's not that, you know, the oil is made of a blue color and a red color and an orange color. It's that the light is bouncing off each of the different surfaces and shifting its phase such that in some cases it destructively interferes with certain frequencies, i.e. certain colors, and other frequencies it constructively interferes, so that white light that was truly made up of all the colors of the rainbow is only allowing certain colors to get through. So that's called the thin film problem, and you can look that up in your book. If we went in great detail in that particular chapter, we would go over covering under what circumstances would the phase of the wave change when it went from one medium to a next, or one media to a next. And then we could add up all that and we'd know exactly how much the frequency was off, and we could tell exactly what colors came out of it. So this wave on a string is acting analogously to light hitting interfaces between various density liquids that are floating on top of each other. And of course, they're floating on top of each other for the same reason that oil floats on top of water or on top of vinegar and oil and vinegar dressing. Okay. So now let's see if you can take the next step. This is something weird. So there's a rope. If you're, for instance, a merchant marine or someone in the Navy or something like that, you might be aware of really big ropes called hawsers. And I think the spelling of that is Hawser. Okay, so you imagine a really big rope called a hawser connected to a really small rope called small stuff. That's literally the name of it. And now you have a hump on the small stuff moving that way. So this wave is going to travel and come to this interface. What do you think is going to happen when that very light string, let's say it's maybe a centimeter in diameter, whereas this stuff has a diameter of, say, 4 inches, and this has a diameter of, say, 1 centimeter. Obviously, that hawser is much heavier, right? So what do you think is going to happen when that wave, that little pulse of wave on the small stuff reaches the connection point of the hawser and the small wave and the small stuff? Anybody? Do y'all see that this is somewhere between these two guys? In other words,
Yeah,
if yeah, go ahead.
Sorry, doesn't it oscillate but like in different directions?
Yeah, so what happens when you get here is this hawser has the ability to actually ripple a little bit. So it's going to actually ripple to some extent, but also it's going to send the small stuff into a ripple upside down.
Oh yeah, that's what I was saying.
Because the hull, yeah, I figured that was sort of what you were thinking of, especially in the Navy. You've probably seen this happen in real life, so that might help as well. But yeah, so when when the pulse gets to the interface between the heavy stuff and the small stuff, the heavy stuff, if it, for any amount that it gives, it's going to act as if it were the sleeve, which is the bottom part down here, right? So that hawser is going to move just a little bit up and down, and therefore that's going to cause an up and down wave moving to the left. However, the little bit of reluctance it gives it, that's going to create a negative wave, an upside down wave in the small stuff and send that backwards. Okay, so that's some of the quote unquote neat stuff that can happen with waves on a string and various things like that. If you, let's talk about the next topic now. Anybody have any questions on that interactions of the strings? Okay, standing waves. So if you imagine you had, say, a wave on a string and you give it a little pluck. If you pluck it just right, then you can keep a wave going back and forth, back and forth, back and forth between these 2 points. So this could be, for instance, the bridge on a violin. And this could be the nub on a violin. Of course, it could also be strings on a cello with the bridge and the nub or whatever. The main thing is they're points that don't move, and they're called nodes. Actually, I shouldn't put a E on that. I mean, an S on that, excuse me. So this guy's a node, that guy's a node. And if you do it just right at the slowest frequency you can, in other words, you're going to start shaking it like this, and you're not going to get anything happening, but you shake it a little faster, a little faster. The first time that it comes to looking normal, what you'll see it happening is the way, whoa, forgot to take it off eraser. That's not good. What you'll see happening is the wave will be up this way. And then the next second, you'll see the wave being down this way. This length right here, L, is the length of the string. And what you'd say is, because remember I said the sine wave is an archetypal wavelength, you can see that this L is in fact 1/2 of a wavelength. This is called the fundamental frequency. So when you pluck a guitar string, that's the most prominent string note you'll hear. And it happens to be, remember, if you look at a guitar or a violin or a cello, basically all the strings have the same length. L1 equals L2 equals L3. In the case of a violin, there's only 4 strings. In the case of a bass guitar, there's only 4. In the case of a guitar, there's 6 or 12, so on and so forth. But if you keep going, increasing the frequency more and more and more to look for another pattern, then the next pattern you're going to get would be this one. Notice now you have 3 nodes, and the length is in fact 2 lambda over 2. This is called the first harmonic. Okay. And if you go even higher frequency, in other words, you whip your hand up and down even faster and get it till it hits that nice resonance, then what you're going to get is this followed by this. In this case, you've got 4 nodes, and L is equal to 3 halves lambda. And this is the second harmonic. That's when we're referring to the frequencies, by the way. Dot, 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 L is going to equal to N lambda over 2 for the nth harmonic. Okay. So you can imagine the next one, of course, is going to be 4 lambda over 2. So that'd be 2 wavelengths. And the next one will be 5 lambda over 2. That'd be 2.5 wavelengths, so on and so forth. And that's actually what you're hearing when you play a guitar. And it just so happens that that fundamental frequency, let's say that's 125 hertz. Well, the first harmonic would be 250 hertz. And the second harmonic would, in fact, be 3 times 150. It'd be or excuse me, 2 times 2. Yeah, excuse me. So that'd be 4 times 125 hertz. So that would be what, 500 hertz, so on and so forth. So that's what standing waves are. And that's for a particular case where you have nodes on each end. If you want to play, for instance, an organ pipe or a Pepsi bottle or a, any kind of glass bottle, basically, that's closed on one end, then this end is a node. And this end is an antinode. By the way, that's an antinode. I'll just write AN. And that's an antinode, and that's an antinode, and that's an antinode, that's an antinode, and that's an antinode. So halfway between the nodes are antinodes. So in this case, the fundamental would really just be a wave oscillating like that. And you can see in this case, L is equal to L is equal to 1 lambda over 4. If you tried the next case, it would look like this. It would say and then, of course, that one would be L equals 3 over 4 lambda. And then the next case would be like that. Of course, I'm not drawing the same size. That would be L equals 5 lambda or 5/4 lambda, so on and so forth. So the things get kind of jacked up when you have a one end open organ pipe. If, however, you have a double open organ pipe, then the fundamental is this, where L is equal to 1/2 lambda. You can see that's a 4th on the bottom and a 4th on the top. Then you have L is equal to, now you've got a 4th on the bottom, a 4th on the top, that's 1.5, so that's 3/2 lambda. So you can see dot, 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 you're going to get L is equal to N over 2 lambda, which is the same thing we had before. Okay, so the double-ended, open-ended organ pipe acts just like the wave on a string, where the ends are tied down. Now, what does all this mean? Well, remember, velocity is equal to frequency times wavelength. And for, let's say, a wave on a string, well, that was horrible writing. I probably should have just erased that. For waves on a string, and I'll say violin. Again, it doesn't matter whether it's a violin or a guitar or whatever, but just violin was the easier word for me to write. What we know is lambda is going to equal 2 over N times L. And the length is fixed. The velocity is the square root of the tension divided by the hey man, don't do that. divided by the mass of the string per unit length. So that's also going to be fixed on a given string. So what you have is V equals F lambda fundamental, and that would be frequency fundamental. That gives you V constant is equal to F fundamental times what I told you was lambda was 2L over N. So in this case, N is equal to 1. So F is basically, in some sense, velocity over 2L. That's the fundamental. Okay. Now, if you look at velocity equals first harmonic, wavelength first harmonic, that means V, the constant, again, the same constant we had before, is equal to F, the first harmonic, times, in this case, it becomes 2L over 2. So the frequency is actually going to be V, whoa, just switch to eraser again. N was equal to 1 there. And this is F U N. Okay, so F for the first harmonic is going to equal V over L. So F first harmonic is twice the fundamental. That's what I claimed earlier. So that's me just showing you that, because the velocity has to be fixed. You're not going to change the tension in the string while you're playing it. That's what you do to tune it, but you're not going to do it after you tune it. So you adjust the tension. You're not going to change the material that the string's made out of, because you're going to be using the same string over and over. And obviously the string with the low mass per unit length, which is the little thin stuff, that's going to in fact have a higher velocity for a given tension. A higher velocity for a given tension, because the mass per unit length is smaller. So that higher velocity, but with a fixed length, means that the frequency is going to have to be higher. So the thin string makes a high pitched noise. Does that make sense? You can do that too. You can compare the first harmonic with the second harmonic. We say V equals F first harmonic times that one we just turned out to be 2L over 2. So F first harmonic turned out to be V over L, which V is a constant. Now V equals F second harmonic. In this case, it's going to be 2L over 3, because the second harmonic is actually N equal 3. We look back here. So notice when we did this one, the first harmonic was N equal 2, or excuse me, N equal 2. The second harmonic was N equal 3, and the fourth harmonic would be N equal 4. The nth harmonic would be N. So the second harmonic would be 3 in this case. So we could say that in fact F second harmonic, that really went to crap. Is going to equal 3V over 2L. So you can see that second harmonic as is related to the first harmonic, F second harmonic divided by F first harmonic would equal 3V over 2L divided by V over L. And of course, that just gives you 1.5. But if you compare that now, and this is, you probably heard me say, I did 125 and then I said 250. And for a second, I said 375. And I said, wait a second, is that 4 times? Here's where we work that out. So if you take F second harmonic and divide it by F fundamental, what we had was F second harmonic was in fact 3V over 2L. But the fundamental, when we looked at that one, oh, there it is. It's just V over 2L. So this becomes 3V over 2L times 2L over V. So you end up just getting 3. So if we multiply the fundamental times 3, which is the 375 is what I told you, you'd get the second harmonic. Okay, so that's some of the kind of neat little mathematics you can play with, and it's just integers and multiples of fractions and stuff like that. That's sort of what's neat about this. It's not that hard of mathematics, but now you sort of understand, and at least it helped me to make sense of how I played my instrument when I was trying to learn the violin. But at the same time, it made me a horrible musician because I had to think out the physics of each of it instead of just knowing which way it went. So for instance, she would say that you're kind of high pitched, okay, on my violin, because the violin is a non-fretted instrument. In fact, I'm so dumb at music, I took the violin as the first instrument I was going to play, because clearly 4 strings is easier than 6, which is what a guitar had. So I got the 4-string instrument, but then realized it doesn't have frets, and the frets are actually where you can pinch off the string. Instead of the string being a constant length, like I told you it was, it always is until you get your fingers involved. When you get your fingers involved, the lengths decrease depending on whatever fret you're on. With a violin, you don't have frets, you just got to play it by ear. So I even went as far as taking some white out and mark little frets mathematically along my bridge, or excuse me, along my neck, and it didn't help me much. I just was horrible. But anyways, if she told me that my music was a little high pitched, she'd use all sorts of words, but high pitch meant high frequency. So I would think to myself, okay, that means I need a lower frequency, which of course is a higher wavelength. And that means, of course, a longer string. So I'd push my finger out towards the thumb board, or the board where you had all the nuts on it and stuff like that. As you can tell, a 3 to 4 second break in the middle of a song is not acceptable music. So so it was not very good at all. Anyways, anybody have any questions on that sort of stuff? Believe it or not, the only thing we haven't covered is what you guys cover in lab next semester, and that's refraction and diffraction. Refraction is where light enters, say, coming from the air going into the water. If you're sitting on the side of a pool, you look down, you see a penny on the bottom. It looks like the penny's closer to you than it really is. And that's because the light coming from the penny came up at some angle. And then when it went from the water to the air, the angle switched. And the reason it switches is something called Snell's law. And Snell's law says that the index of refraction of water, N sub W, say, times the sine of theta in the water is equal to the index of refraction in air, so that'd be N sub A, times the sine of theta in air. And the water, in fact, has a higher index of refraction than does the air. Air is essentially that of a vacuum, which is about 1, maybe it's 1.01. Okay, but where water is like 1.5. And because of that, the light actually bends farther from the normal when light goes from water to air. So let me show you an example of that. I've essentially covered all of this, but here's the part I was talking about. So let me stop sharing this screen and let me start sharing this other screen. Okay, so you can imagine rows of soldiers walking on firm ground and then running into mud. This is a really good example. So you imagine that diagonal line that connects each of their heads. That would be, say, the crest of a wave, and then that next one would be the next crest of the wave, and the next crest of the wave, and the next crest of the wave, and the next crest of the wave. When you go from something that light goes through quite fast, in other words, it's easy to walk on firm ground, then you're just going to keep going straight and no problems. But as your soldiers on this end start to get slowed down, i.e. the end of the light waves that are going into the mud, or in this case, mud, but in water, in the case of light going into water, it would be water. Those guys are going to start to slow down, and therefore they're going to bend to an angle that's closer to the normal. In other words, this theta 2 that you see here is smaller than this theta 1. Now the equation, Snell's law, says that the N for air, which is essentially 1 times sine theta 1, is equal to the N for water times sine theta 2. And you can look up, for instance, what the index of refraction for water is. And I think they told it to you up here. I thought they would have gave it to you here, but I guess they did not. Maybe they did it there, but it was lower down on the page. Nope, they did not. So the index of refraction for water, if I remember correctly, is 1.5, but I sometimes mistake it because there's another one that's 1.3. I think glass is 1.3 and water is 1.5. But that's the way light or waves can interact when they change materials. So that's sort of like the thin lens stuff I talked to you about earlier. If, however, light's coming from the water going to the air, then the angle gets bigger. So you're used to light traveling straight. So if this is the beam that your eye is seeing, you think the penny on the bottom of the pool is right here, when in fact it's way down here, because you're expecting light to travel in a straight line, but in fact light went this way till it got to the water, and then it bent over and went that way. So that's why the water looks so shallow from the side of the pool. So that's one thing that can happen when light interacts. I've told you about how light interacting going into oil and then water and all that sort of stuff. This is part of that. Refraction would go on, but when you're talking about really thin stuff, the amount of bending of the angle is irrelevant, because the layer of water or the layer of oil is so thin, the angle is irrelevant. There's another thing that happens called diffraction. And basically this fundamental rule is what you want to know. As a rule of thumb, only if the wavelength is smaller than the size of the object will there be a significant shadow region. So if the wavelength is smaller than the size, so what we're doing is imagine the wavelengths of these water waves. So you can see it's about that distance right there. That's the wavelength of the waves. Now, if that happens to be smaller than the size of the object, like in this case, notice the object is quite big, then you'll get a shadow. In other words, the light cannot bend rapidly enough around this to cause it to have waves back here. So you end up getting this triangular shaped shadow region that's quite long. However, in this case, the waves were markedly larger, a little bit larger than the object. So there wasn't any significant shadow. And in this case, they were really quite a bit larger. So of course, there wasn't much of a shadow there either. But it turns out whenever light interacts with an edge, it's going to bend. And in the best case scenario, like in say Hubble or James Webb Space Telescope, the diffraction that happens is directly proportional to the wavelength of the light. So infrared being longer than visible light means that infrared is going to diffract more. But the other thing that it relates to is really how big is the wavelength, and then how big is the length that you're going away from it. So diffraction happens on everything. It causes light to go through a rectangle and makes it look kind of round as opposed to a rectangle. But the main thing is diffraction is something that's going to happen. And it's what makes the edges not look so pristine when you shine light through a hole or through a rectangle or something like that. That's it. I think we've pretty much done everything. 2L over N, you see that, diffraction, refraction. Remember, reflection is it bouncing off, and reflection angle is equal to the incident angle. Reflection is what I was just talking about there. But when it pierces a surface of another compound, then it's going to refract, R-E-F-R-A-C-T, and then there's diffract, which is what it does when it runs around an object comparable in wavelength, or if the wavelength is even smaller than the object, it'll do weird things. Okay, so all of this chapter is mostly simple applications of concepts by doing stuff like, just applying Snell's law, which is that equation that I just talked to you about. N1 sine theta 1 equals N2 sine theta 2. And by the way, N is just the speed of light in the material divided by the speed of light, the speed of light in vacuum divided by the speed of light in material. So when you say N1, what they really mean is, or like say N in the water, what they're saying is, what's the speed of light in a vacuum? That's 299,792,452 meters per second divided by the speed of light in water. And what you're going to find is that's considerably smaller. So you get like 1.5. You can see in this case, they say two waves traveling in opposite directions on a string fixed at x equals 0 are described by the functions here. So just looking at this, you should be able to realize, oh, evidently the k must be 2.0 for this D1, and the k for this D2 is also 2.0. So these two have the same wavelength. Also, the omega is 4.0. And the omega here is positive 4.0. So what this is telling you is this D1 is going to the right and this D2 is going to the left. They both have the same amplitude, because that's 0.2 meters right here, and the same amplitude here, 0.2 meters. And they say, and they produce standing wave patterns. Determine A, the function of the standing wave, B, the maximum amplitude at x equal 0.45, C, where the other end is fixed, x greater than 0, and D, the maximum amplitude. So you can see a lot of this is just about you recognizing, oh, this is A times, in this case, they use sine instead of cosine. That's okay. Kx minus omega t. That's all you're doing on these types of problems. It's pretty straightforward stuff. Piano string. A piano string is 1.10 meters long and has a mass of 9 grams. That means you can take 1.0 or 9.00 grams, convert that to kilograms, which would be 0.00900, divide that by 1.1 meter, and you've got its mass per unit length, the mu that we were talking about. How much tension must the string be under if it is to vibrate at a fundamental frequency of 131 hertz? Well, fundamental frequency, we know the string is going to be basically half a wavelength long. So we now know the wavelength of it. And then all we have to do is solve for the tension, because we have the velocity, which is the square root of the tension divided by the mass per unit length. We've got the frequency that they gave us. And since they gave us the length, we can readily figure out the wavelength. Because it's a fundamental frequency, the wavelength is actually twice as long as the string. So you see how it's if you understand the concepts, the problems are pretty straightforward. Hopefully that'll help you guys. Anybody have any questions about this stuff? All right, I'm going to kill this and just tell you, I made an announcement at the beginning of this video in case anybody came in late. I will recap that right now. So practice test 5 is staying open until July 25th, but that's kind of a screw up because test 5 is a purely online test that you're allowed to use the internet, your notes, your book. You're just not allowed to communicate with someone directly about it or to look at any document created after I opened that up, which was like last week. But it has to be done. All the trials have to be done by 11:59 p.m. Sunday night. That's test 5, which covers 10, 11, and 36. The practice test will disappear essentially at the same time. Right now it's saying the 25th, but I may or may not change it. I don't care that much. Now, the next test, test 6, that practice test is already open. And the one you're going to hit many times is called practice test 06, chapter 14 and 15. Let me go ahead and share the screen with you on this one because this might actually help you a little bit. So you can see this is the practice test for test 5. I put that up last week. As I said, it should really disappear at 11:59 on July 24th because you see July 24th is the due date for test 5. Okay. Test 6 is sort of online. It's going to be online in the sense that you can take it whenever you want to, but it's not going to be online in the sense that you're going to be monitored. One, you have to have Respondus lockdown browser on. 2, you can't have like your cell phone near you. You can't be running in and out of the camera. You can't be doing a lot of work up under the desk. That's going to flag you as cheating. And then I got to go watch the video of you, which it saved of you taking the test, that sort of thing. So you're going to take that test 6, as you can see right here. It has to be done by August 1 at 11:59 p.m. Okay. And it's going to be done with the Respondus lockdown browser and a webcam. So you've got to make sure your computer can run the webcam and the Respondus lockdown browser. To do that, I've given you a separate version of the practice test 6 that doesn't mean anything because it actually has that extra chapter that we didn't cover. But the main thing is you want to go through it probably tonight or at least first thing tomorrow and just make sure you have an up-to-date version of Respondus lockdown browser and that it works with your camera and all that good stuff. Okay. Now, what that means is on the 27th, which is Wednesday, you have your first chance to take the final, and that will be during your lab period with Mr. Mitchell. If you wish to take it that day, that's great. Just show up at 2:15 and no later. Okay. You will be allowed to take it in a face-to-face format. You will have probably a lockdown browser in there as well because we've had some students taking advantage of the system. So I've had to do this lockdown browser thing. So we'll have that lockdown browser for that one. You're also, if you don't want to take it on the 27th, you can take it on August 3rd, which is a week later, again on Wednesday. Those are your 2 dates to take the final. Any questions on that? All right, you folks are free to go. Thanks for coming tonight. And I'm sorry about all the headache with changing these dates and stuff at the last moment. And make sure you, email me if you're having any problems. We did fix the practice test 5 issue. Namely, I had changed one version of practice test 5 and y'all were taking the old version of practice test 5 that no longer was available. So that's, mea culpa. So sorry about that.
Professor.
Yes, ma'am.
Oh, sorry. I always interrupt and I don't mean to, but
Okay.
on my lab and mastering, I think you meant to push back all of the homework that we were doing, but one of the conceptuals stayed back for last week, so it's past due now, but I think it was supposed to be due this Saturday.
Let me fix that right here in real time. I'm cooking my lab. Everybody, you guys are free to go. If you have any questions for me, I'm going to wait for the last person to leave, but you are free to go. I'm going to open up my lab and mastering and adjust these dates because I have one of them a student told me about was conceptual 36. Is that the one you were talking about?
Yes, that's it. You can see the recently due how it's at a bad average score. That's probably because we need it to be extended.
Okay, yeah, let me do this. This should have been 3 days from Monday. Monday was the 18th, so I'll just be nice and push it to the 24th.
Okay, sweet.
Okay, so I got that fixed. Did y'all see I had to check real quick and make sure I didn't have anybody's grades up here. No, I don't. Okay, that scared me. Okay, so these are
No.
like class averages and stuff. So everything's looking good for
Yeah.
there. I can go over here to instructor tools and do assignments, and then that'll show me all the due dates, and I'll just check and see if anything else is amiss. It looks like conceptual 15 is 7/24, so you still got a couple days. That makes sense because we just covered chapter 24, or excuse me, chapter 15. Today's the 20th. That gives you 4 days. I think that's reasonable. It's not that hard of a chapter. Chapter 14, where the heck is it? Okay, chapter 14, 7/24, so that's fine too. Do y'all think y'all need a couple extra days? I can give you a couple extra days on 15 if you think you need it.
Yeah, we might because we're doing practice tests for the next test and stuff. So it's gonna be like a mix of both.
Let's make it the 31st.
Thank you.
No problem. Yeah, I don't mind working with you guys. I know I'm a slacker sometimes, so at least I can do is help you. Let's change this 14. I'm going to change that to 31 as well. I'm going to change this 14 up here to 31. I don't want you to wait that long because you'll have already, taken the test. You really need to do it before you take the test. So I've now got 14 and 15 for 731. And here I've got 14 for 731, but not 15. So I'm going to change that to 731. So that should give you plenty of time. All these are extra credit. You're completely welcome to do. And in fact, I'm going to change them now to the 31st in case people want to try to earn some extra credit. I just don't want them due after you take the final, because I don't want to have to go back in and regrade stuff. And this is like this one, 31, 31. That one's already 31. That one's already 31. There you go, my peeps.
I think that's it. And the other question I have is concerning the lockdown browser, because I used one for calculus this semester and I got a violation because I had my formula sheet below my camera. Like, for instance, it wasn't pointing down at like my desk while I was working. And that's because I couldn't see the laptop with it like that.
Okay, gotcha. Down it actually on your
I don't know.
laptop.
Right. If that becomes an issue with this one, are you still able to like look back at the video and like check us
Yeah.
off for it, or is that going to be something?
Yeah, I can look
Okay.
in it at any time.
That was just.
and it even tells me like the time interval where you did something funny. So I'm going to, in fact, I don't think I put it in this one, but I have a more pressing version of the instructions of what you're supposed to do. So you're going to take your laptop and you're going to take the camera and aim it at the work area around you, everything that's in arm's reach of you. And you're even going to show me both sides of your equation sheet and any blank paper you have and that sort of stuff. So even if you were looking at that, I would know better than it being a problem. So just, keep that in mind. It'll be like that, but I got to put those instructions in there because it doesn't have it yet, but I want to put it in the practice one as well as the real one. So you'll have a real feel for what it is.
That makes sense. Yeah, that's not what it was like with the other one, and it was just like a big mess. And they were like, "You get your active," and I was like, "What the heck is going on?" But yeah,
Gotcha.
So it should work out.
Yeah, that should be fine. Josiah, I see you had a question about what was that thing that looked like a G. It's actually the Greek letter phi, P-H-I, but they pronounce it like P-H-E-E. And the way I write it is I do a circle and then I go vertically down through the middle and do a little curl like that. So it's almost like theta turned over on its side, but that's just a typical symbol we use for the phase angle.
Okay, thank you. I was also going to ask, is there any information that like, if we had it on our equation sheet, like, okay, so if we have a non-equation aspect of physics on our, what is it? These like sheets,
Equation sheets,
will
yeah.
that disqualify us as in like a law?
Yeah.
If we have a law written out?
Yeah, because like one of the things I sometimes throw in is what I call chucker questions are state Newton's first law of motion, state Newton's second law of motion, state Newton's third law of motion, state Kepler's first law, Kepler's second law. So if you have any sentences written down there, that could be a problem. Or really all you're allowed is the equations that have like 14-11 next to it in the actual textbook. So
Yeah.
yeah, don't write your laws and stuff like that, because I use those as what I think is me giving you a gift, because every student that takes physics should probably realize that maybe Newton's laws or something that you might want to commit to memory just in case. And they're supposed to be super easy. Obviously, if you had them, they're really easy written on the sheet. But if you didn't learn them, then there weren't. So I've been trying to warn people about that for the last couple of weeks. But yeah, everything that you had that was called a law, like conservation of linear momentum. When is that true? Conservation of angular momentum. When is that true? Conservation of energy. When is that true? And then Newton's first law of motion, Newton's second law of motion, Newton's third law of motion, Kepler's first law of planetary motion, Kepler's second law of planetary motion, Kepler's third law of planetary motion, Newton's first principle of relativity, Newton's second principle of relativity. Remember, the first one was the laws of physics are the same for all inertial observers. And then the second one was the speed of light is a constant independent of the motion of the source or the motion of the observer. So all those things are like fair game. So you don't want to have those written down. Okay. You're allowed to have equations written down. You shouldn't have any, you can have any constants that you want. Like if you need the gravitational constant, or if you need the mass of a proton or something like that, or mass of an electron. I'm hoping the manual will have it the test will have it. If for some reason one's forgotten and it's a constant, like you can look up in the front of the book, which would be G 6.67 times 10 to the negative 11th, or G 9.8, or the mass of an electron, or the mass of a proton, or the mass of the earth, or the radius of the earth or sun, or any of those things. You can ask Mr. Mitchell for that, and he'll know that he can give them to you.
Okay, thank you.
Anybody else? This will be posted tonight as soon as I get it done. So it just takes a little while for it to download and upload. Nora, you
All
have
right,
anything
thank you,
else?
Professor.
You're welcome.
Nope.
Thank you.
That's all.
Have a good day.
You too.
Bye-bye.